Hi, and welcome back to this, the 25th anniversary episode of me repairing, overhauling, converting, CNCing this old Sieg 7x12 mini lathe. To celebrate that it's the 25th anniversary episode, I've decided to shoot this in 4K. Now for those of you who are still stuck with the Imperial system, what that means is you get 1K for each 1 6 1/4ths of the series. I'm not exactly sure whether my laptop can render 4K video, so I better give that a check before I get too deeply into this. In the comment section from last week, a couple of you picked up that I'd made a bit of a mistake in the configuration. I had the number of pulse width modulation generators 0 for some reason, so that was definitely wrong. Okay, this just keeps jumping back to 0. It looks like this function hasn't been implemented in PC in configuration. Which is probably quite normal. This is a non-standard firmware I'm using for the Mesa card, and they've probably only implemented the standard configuration in this configuration program. This is quite normal in the setup of LinuxCNC. This program, you normally only use it once, get a basic HAL and INI file, and then from there you normally continue with manual editing. So if we look here in the Minilathe folder, we'll see that there's a Minilathe HAL file, hardware abstraction layer file, and a Minilathe INI file. And these are the two that we mainly edit to get all these sort of things working. So if we open the HAL file, what can we see here? It was generated automatically, and as it says, once you change this file, it would be overwritten by it if you reuse the PCN conf, so I won't be using that anymore. We're loading a bunch of different software modules. By the way, LinuxCNC was originally called EMC, that's why you sometimes see these old references. HostMod2 is the interface driver for the 7i96 Mesa card. Ethernet board, number of encoders, number of pulse width modulation generators. We just need to edit that to 1, so I'll save that. And we can see whether that actually works by starting LinuxCNC. Going up here and opening the HAL show. The HAL show gives us a chance to look at the status of every pin and every signal on our system. So what we should have is a set of pins created by the 7i96, and there should be encoders. There we go, there's our pulse width modulation generator, and there's our step gens. So we can see that the firmware is good. We've got all the necessary firmware connections to control everything. So next it's just a matter of making these things talk to each other properly. What I'll do next is wire up the physical connections, the physical wiring, and we'll get back and get it working. First up, I need to connect the 19 volt DC into this board using a mirror written on the bottom of the board. This is the ground pin and this is the power pin. Here's the wiring diagram I've made for the connection of the VFD through the little analog control board to the 7i96 Mesa card. Now that I've made up some cables, I can start connecting up the Mesa card to the pulse width modulation converter. Now on the Mesa card, I've got, this is terminal block number 2. Okay, and these go down to ground. And pulse width modulation input. So these wires should each go out into the cable canal. I probably should have done that before I connected them. So next up, we need the 0 to 10 volt output. That's ground and V out. probably not strictly necessary to wire twist a pair of wires holding a DC current, but who knows? Maybe it'll help reduce the EMI if I do this. I guess there's no real downside of doing a twisted pair. Maybe there is. I don't know anything about electronics, so I'm sure someone with more knowledge is going to put a comment in the comment section reporting that this is actually a bad idea. Oh well. And then this end of these wires get connected to the VFD, but first I think I'll connect them to the multimeter and just check whether I can actually control that signal. In the last episode, I downloaded and flashed this board with the software to provide one pulse width modulation generator. Now, because I'm only using 2 out of the possible 4 step generators, I now don't know on which pins the Mesa card has assigned the pulse width modulation signal that I need, the one that I'm going to need to connect to this little board. So to interrogate the card and find out where it's assigned that signal, I need a program called Mesa Flash. PCW pointed out the way to install Mesa Flash on page 15 of my build thread, which is on the LinuxCNC forum. So basically just go to the GitHub, you'll see down the bottom there's some clear instructions. So first install this library. I needed to install Git as well, clone Mesa Flash, switch directories, build it. I didn't bother with the help because I already had the command in that file. And then finally you just run Mesa Flash, and in this case run Mesa Flash with this. So I'll open a terminal window and do that. Okay, and here you can see it's interrogated the processor and given us all we need to know about this thing. And what I'm specifically looking for is the pulse width modulation output. And here it is here. It's been assigned pins 5 and 6 on the connector TB1. What I find kind of interesting is that TB2 is then and TB3 are not assigned anything at all on that build. I wonder what's happened to all my I/O. It's taken me a while to get my head around the pulse width modulation output part of things. Turns out that I needed to connect between pin TB3 is the positive pulse width modulation pin, and then a ground being like pin 1. So just to test the signal, I've got the HAL show set up, and if I put in a value of say 10%, which would be about 270 RPM, and you can see I've got about a 10% pulse width modulation value there. Let's go up to say 500. It gets wider. Let's go to 1500. It's looking good. And maximum should be 2715 according to the scaling I've set it for. And as you see, then it's just a constant whatever 5-volt output. So the output from the board is looking good. That then comes into here, and we should now get DC voltage coming out of this out of these lines. But as you can see, we don't. We've got our signals coming out of here into the board. The board will then, the board's receiving 19 volts and should send a 0 to 10 volt DC signal down this line, which I've connected to the multimeter. So hopefully I can now get some voltage control. Okay, now I see it. This is ground, and I've got it connected to this pin here, which is actually the positive pin. So I've got those two reversed. Yeah, I've set them full scale to be 2715. RPM. So if I set 2715, I should get 10 volt. Okay, let's try a different value. Let's drop down to 1/10, which would be 271. Should give 1 volt. Okay, it's a bit high, it's 1.3. But obviously the system is now working. Let's go for 342 volt, which would give us 2 volts. Okay, it's not very linear down there. 1350 RPM should be 5 volt. Once again, it's a little bit high. So 5 volts, full scale, 10 volts, 1/10. Well, that's looking pretty good. 20%. Okay, that's really looking good. That should be 40%, 4 volts. That's now installed and tuned. Now we've got to try and do is work out how to get, on the one hand, how to get LinuxCNC to drive the signal, and on the second thing is we need to get the signal to come out of here and feed the VFD. I've just hooked up a jumper for the enable of the VFD and hooked up another jumper just to turn the motor on. That's at about 50%. Now we'll just give it a speed command of 10%. Okay, that's actually running at more like 20%, so let's give it a speed command of full speed. Well, it looks like I've set up the VFD for full speed command is equal to 100 Hertz, whereas of course line frequency here is only 50, so I need to adjust the scaling to make sure that this runs the motor at the correct speed, although I might even leave it at that and just adjust everything else and accept possible high speeds. I guess we'll see once we've got it on the lathe. Based on that, maybe I would have been better off putting a smaller pulley on here, but it is following the speed command, so that's good. What that means is that our little pulse width modulation board over here is correctly wired up, attached, everything's working perfectly. I just need to change the numbering on the wire there. One of my wires has got the wrong signal identification on it. So I've tested this part, that's working fine. Now I've connected 3 of the output switches from the Mesa card to control the VFD's enable signal, and then its forward and reverse switches. Unfortunately, I've got this problem. As soon as I connect a signal, it immediately goes active. And that's although the switches on the 7i96 are actually off. The switches are working correctly on the 7i96, because if I do a state change, you can see the lights going on and off. I've now set up the multimeter on the across this switch, which is switch number 0. As you can see, when it's in the off position, being some sort of electronic solid state kind of switch device, it's not actually an open circuit. It's got 2 megaohms of resistance. And then if I switch it on, we'll close the circuit, light comes on. Now the problem I've got with the VFD is that that off signal is not off enough. I'm guessing that there's enough current flowing to still activate the VFD's enable function. I did a bit of internet surfing and I thought maybe it needs a pull down resistor. So I've put a 1K resistor between the switch output, I guess switch input in that case, and the earth of this device. Didn't change anything. So if anyone's got advice of how to fix that, I'd appreciate it. So while waiting for some feedback on that problem, I think I'll connect up the encoder and try and get that working. This is my encoder here, and it says it accepts between 5 and 24 volts, and I think the Mesa puts out 5 for an encoder. It says it's an NPN open collector output, which means absolutely nothing to me, but I'm sure someone can explain it to me. Down here you've got the circuit diagram, so the brown wire is positive, the blue wire is negative or ground, and then it's just a single-ended output of black being A, white being B, and orange being the index signal. So that should be quite simple to connect. Now if we compare that, in our manual for the Mesa, we are single-ended here, with the jumpers 2, 3 and 4. In the left-hand position, we're in the single-ended mode. Jumpers 2, 3 and 4 must be here somewhere. Okay, jumper 2, jumper 3 and jumper 4. So each of these 3 jumpers gets moved over. Left hand being this side, according to the diagram. This must be encoder A, ground, encoder channel B, power, and then index. Okay, that looks easy enough. I'll do a quick wiring diagram on that. We now mark our wiring. TB2-7. I'll extend the shielding here with just a normal grounding cable, and this will then be connected to the star ground with all the other components. Okay, now that we've got the encoder connected, let's make sure it's actually working. So we'll go and have a look in the HAL show. Pulling up the pins, the 7i96, it's encoder, it's the encoder number 00, there's only one, and let's have a look at the counts. Now if we move the encoder, you can see it counts down, counts up, so that's looking good. If we look at the inputs A and B, they click backwards and forwards as you move. Moving a little bit too fast to count them. As the encoder seems to be working normally, I'll unplug that and put it out of the way. As you can see, I've wired up the stepper connectors on both sides and the power connectors to power this board. Now the last thing I'm going to add is a capacitor across the power terminals. According to the Phytron ZMX driver manual, it does recommend putting in a 47 picofarad 100 watt capacitor across the leads if your leads are longer than a ½ meter. Okay, mine probably aren't quite there, but they're getting close. And I found I had this 1 microfarad capacitor, 100 volt. Now I think this capacitor was left over from either the guitar amplifier I built from a kit set, or more likely it was from when I changed the capacitors on the Indramat servo drive unit for the Mahu. You know, the thing was 30 years old, so I went through and just replaced capacitors before anything blew up. Oops, I just realized I put that capacitor in back to front. That end there is the positive end, but this is the positive terminal. This is the data sheet for the motors I'm using. They're these Keeling, pretty high torque stepper motors. And I'm wiring them up for bipolar parallel, which means that they can take 4.2 amps per phase. These Phytron drivers max out at 3.5 amps though, so I won't be driving the motors quite at their maximum power. So I want the full 3.5 amps, I need to set it to F, and also I want 1/20th micro stepping, which comes up twice, so I could either set 7 or F. Found this artwork of my backplane adapter. That's the step signal and that's the direction signal. Those are the only ones I've actually bothered to connect by the looks of it. That means I've put all of those 4 wires along in a row. These other wires coming off here are... okay, this was just a jumper between one breakout board to another breakout board. That's not relevant for this usage. So really I've only got these 4 wires to connect into. So I'll probably just butcher my existing ribbon cable and just break out those 4 wires. Each individual wire that I'm using, I've kept it a pair with it just to provide a little mechanical stability to it. So this connects to TB14. Now with everything connected, let's see if those motors work correctly or are set correctly. They're definitely powered up because they've locked. Remember, we have different jogging speeds because the lead screws are different on each, so the RPM will be different. Okay, that's too fast. Yeah, I'll have to set that up once I've actually got the motors installed and have all the kinematics of the whole lead screws and that. I'll have to revisit what are the maximum speeds this system can run at, but as it's currently set, everything's connected correctly electrically. I guess it's time now to break all this down and install it on the machine. The ground studs in these cabinets are way too large for what I want to use. I think these are M8s. So what I'll do, I'll just make a little bus bar with an M8 on here, and then a second hole with maybe an M4 or something stud, so I can then terminate all of my various grounds in like a star ground. That's lucky. I even found some brass screws and nuts to go with those. Now that I've put all of the electrical components into the cabinets and wired them all up, I'm just going through and testing them. So the first thing to test is the encoder. As we turn, we can see that the encoder count changes in both directions. Both channel A and channel B are working. And somewhere in here, hopefully we'll see the index. Oh, there it is. So the index is also working. Cool. So that's that done. Jogging. Oops, the keyboard's a bit flaky out here. It's a Bluetooth keyboard. But it's working. Jogging's working. Okay, so the only thing that I haven't got working yet is the only thing I haven't managed to get working yet is the VFD's forward, reverse and enable switching. I put a request onto the LinuxCNC forum but haven't got a response on that yet. So if anyone has got any ideas of what I need to do. So next up I need to measure the cable channel covers. So the big one's going to be 26, 12, 19 and about 25. Right, that neatens that up. Next door's back on. Well, I guess the next thing for the scrap bin is the original motor, driver, housing. Won't be using that again. Well, I think that's about it for episode 25. Next week, what I need to do is install the motors, and then I can start looking at the motion. If you have any questions or comments, please add them in the comment section below. Once again, thanks for watching.